Some of the homework exercises involve deducing properties of the shape of a solution curve from the differential equation. Anyway, I wanted to do one like that for you. The graph below shows a solution to one of the following differential equations. Which is the correct differential equation? Let's do some analysis of the shape of the graph and what the shape of the graph would say about its derivative. The first thing I notice is that we've got a section where the graph is increasing, and then we've got a section where the graph is decreasing. And the reason that's important is, remember that when you're increasing, your derivative is positive. When you're decreasing, your derivative is negative. So that gives us information about what we should expect from the y primes in the differential equation that goes with this graph. However, these differential equations also involve x and y. So let's make some observations about x and y on our graph. First of all, it looks like y is always positive. The graph is always above the x-axis. Which is why I'm saying that the y value on the graph is always positive. Oh, and this should have been a y prime over here. Now, if we look at the x values, what I notice is that we've got this increasing section where y is increasing anytime x is negative. So I'm going to just add that in. Y prime is greater than 0 for all negative x's. But we've also got a little section here to the right of the y-axis where we're still increasing. X is no longer negative, but it looks like that happens for, I'm just going to say for small positive x values. And we were not given any coordinates, any scale on our axes, so that's all I can say. I don't know what this x value here is, where we've got the maximum. But that's okay, we won't need to know that. Moving on to the part of the graph where y prime is negative, because it's decreasing, I'm going to say that happens for, I'm just going to say larger. I have to be vague because I don't know what that question mark x value is. So I'm just going to say for larger positive x values. One other thing that might be helpful to notice is that there's one dot here where we have a horizontal tangent, meaning we have a zero derivative. Right there at that one spot. What I'm going to do now is go through each of the differential equations and try to find a reason to eliminate it. So I'm going to use a process of elimination. And what I'm going to do is I'm going to first think about quadrant 1 and what our differential equation says should be happening in quadrant 1, and then compare that to what we actually have in quadrant 1. If I can't eliminate this first differential equation by thinking about quadrant 1, I'll go on to quadrant 2. And if that didn't eliminate it, I'd check quadrants 3 or 4, except that in this problem, The graph only exists on quadrants 1 and 2, so I won't be looking at quadrants 3 and 4 at all. Okay, so starting with quadrant 1, x is positive there. And we said y is always positive. Well, and if we're in quadrant 1, where y is definitely positive. In that case, the product xy is positive, so 1 plus xy is positive. In other words, the solution to this differential equation would be increasing in quadrant 1. And that is not the case for the solution curve we have, so we can reject this one. Let's go on to look at y prime equals minus 2xy. Again, I'm going to start with quadrant 1. So if x is positive and y is positive, then clearly minus 2xy is negative. And that would say that the solution curve for this differential equation would be decreasing in quadrant 1. And I'm going to add a couple of extra words there, decreasing in all of quadrant 1. And that is not the case for the solution curve we are given, because there's that little bit of increasing area in quadrant 1. So this one is not decreasing in all of quadrant 1. So we can eliminate this one. I want to point out one other thing. Even though we've already eliminated this one, it can be useful sometimes to think about where the derivative would be 0. So just as an extra note here, let's notice that for this differential equation, we'd have y prime equals 0 when x equals 0. So my point is that the solution curve to this differential equation would have a horizontal tangent at x equals 0. In other words, where it crosses the y-axis. And the graph we were given does not have a horizontal tangent where it crosses the y-axis. It's going uphill there. So that would be another reason to eliminate this one. We didn't need it for this one. We already had eliminated it, but you may find you need to use this kind of idea of where the derivative would be 0 on some of the homework problems. Well, there's only one possibility here. We've eliminated all the others, so this is the one. Let's at least check, though, and make sure it's plausible. So in quadrant 1, let's see if this would be plausible. So if x is greater than 0 and y is greater than 0, that xy then xy would be greater than 0. So y prime, well, that would be 1 minus some positive number, because 2xy would also be greater than 0. Well, is that going to turn out positive or negative? It depends on how big the number we're subtracting is. If this number is bigger than 1, we'd get a negative derivative. if that number is smaller than 1, would get a positive derivative. So this could go either way. We don't have enough information to know for sure. I'll just note could be positive or negative. And that's actually good because our graph shows areas where y prime is positive in quadrant 1 and also in quadrant 1 areas where it's negative. What about in quadrant 2? Well, if x is less than 0 and y is greater than 0, 2xy is going to be negative, right? Because I'd have a positive times a negative times a positive. So y prime would be 1 minus a negative which of course is the same thing as saying that y prime would be 1 plus a positive number. And if you take 1 and add a positive number to it, you get a positive value. So we can see that the derivative would be, for this differential equation, the derivative would always be positive in quadrant 2. So it would always be increasing in quadrant 2, which fits with our graph. So this is certainly a plausible DE for the graph. Okay, I hope this helps you with those homework problems that involve looking at graphs and picking out which differential equation could go with the graph.